When you hear the words quantum computer, what kind of machine comes to mind? Perhaps you imagine a giant golden structure hanging from the ceiling like an elaborate chandelier surrounded by tangled cables, vacuum chambers, lasers, and control equipment. That image is not far from reality. Many of today's most advanced quantum computers look less like ordinary computers and more like entire physics laboratories. Superconducting quantum computers must be cooled to temperatures extremely close to absolute zero, colder even than the average temperature of outer space. Quantum computers based on trapped ions or neutral atoms also require ultra-high vacuum systems, precision lasers, and careful isolation from vibration. But a quantum technology company in Leipzig, Germany, is asking a very different question. Why must quantum computers remain inside enormous research facilities? Could they operate in ordinary offices, factories, vehicles, or other real-world environments? The company is called SaxonQ. SaxonQ is developing a quantum computer that does not require a dilution refrigerator. It does not need an ultra-high vacuum chamber either. It is designed to operate at ordinary room temperature, with power consumption of roughly 600 watts. And instead of occupying an entire laboratory, the system is approximately the size of a conventional server cabinet. So, has the age of the personal quantum computer finally begun? Or is this still a small experimental device with too few qubits to offer meaningful computational power? Today, we will explore how SaxonQ uses tiny defects inside diamond to build a room temperature quantum computer, how its architecture differs from other quantum computing platforms, and how far we should realistically trust its ambitious vision. Why are quantum computers so difficult to build in the first place? A classical computer bit is either 0 or 1. Information is represented through two distinguishable states, such as current flowing or not flowing through a circuit. A quantum bit, or qubit, is different. Before measurement, a qubit can exist in a superposition of 0 and 1, and when several qubits become entangled, they no longer behave as completely separate objects. Instead, the entire group can act as a single quantum state. It is this combination of superposition and entanglement that gives quantum computing its extraordinary potential. But the same properties also make quantum computers extremely fragile. A small amount of heat, a fluctuation in the electromagnetic environment, a vibration, or an interaction with a nearby particle can disturb the delicate phase relationships that carry quantum information. This loss of quantum coherence is known as decoherence. Imagine a quantum state as a whisper. In an empty, silent room, even a quiet whisper can be heard clearly. But in the middle of a crowded marketplace, the voice of a person standing beside you may disappear into the noise. Until now, quantum computer engineers have mostly tried to silence the marketplace. They cool everything down, place atoms in vacuum, isolate the system from vibration, and shield it from electromagnetic interference. To protect quantum information, they separate it from the outside world as much as possible. SaxonQ takes a different approach. Instead of making the entire world silent, it searches for a quantum state that can survive relatively well even in the presence of ordinary environmental noise. That quantum state is found inside diamond. Diamond is a crystal made of carbon atoms arranged in a highly regular structure. We usually associate the value of diamond with perfection. The fewer impurities and defects it contains, the more transparent and beautiful the gemstone becomes. But in quantum technology, imperfections can be more useful than perfection. Imagine that one carbon atom inside the diamond lattice is replaced by a nitrogen atom. Now imagine that a neighboring carbon atom is missing entirely. The nitrogen atom is represented by the letter N, and the missing atomic site is called a vacancy, represented by V. Together, they form what physicists call an NV center, or nitrogen-vacancy center. This small defect can trap electrons. Those electrons possess a quantum property known as spin. Spin does not mean that an electron is literally rotating like a tiny ball. It is better understood as an intrinsic quantum orientation belonging to the electron itself. Different spin states can be used to represent the 0 and 1 of a qubit. The surrounding diamond lattice acts as a rigid protective framework. Because the electron spin is embedded inside this stable crystal environment, an NV center can preserve useful quantum properties even at room temperature. SaxonQ also emphasizes a co-doping method that introduces sulfur atoms as electron donors. The purpose is to help the NV center remain in the negatively charged state, known as NVR, which is required for reliable quantum operation. According to the SaxonQ white paper, this patented co-doping technique is intended to improve the stability and reliability of the qubits. There is something philosophically fascinating about this. For a long time, engineering treated defects as problems to eliminate. In semiconductor fabrication, imperfections were often sources of noise, failure, or reduced performance. But modern physics sometimes tells the opposite story. A perfectly uniform material may have no special function at all. A carefully designed imperfection can trap an electron, interact with light, preserve information, and become the foundation of a new technology. A flawless diamond is a jewel. A diamond with the right defect can become a quantum computer. Perhaps human life is not so different. The wounds and empty spaces we once wished to erase may sometimes become openings through which new meaning enters. A defect is not always merely evidence of failure. It may also be the place where an entirely new function begins. How does a quantum computer, based on these diamond defects, actually perform calculations? The operation of an NV-center quantum computer can be understood in 4 basic stages. First, a laser is used to prepare the electron spin in a known initial state. This is similar to resetting a computer's memory before beginning a calculation. Second, precisely controlled microwave pulses are applied. By adjusting the frequency, duration, and phase of these pulses, engineers can rotate the electron spin state. These controlled rotations function as single qubit quantum gates. But the SaxonQ quantum node is not limited to one electron spin. Around an NV center, there may also be the nuclear spin of the nitrogen atom and the nuclear spins of certain nearby carbon atoms. The electron spin can be controlled relatively quickly and can be read through optical signals. Nuclear spins, by contrast, are often less exposed to environmental noise and can preserve quantum information for longer periods. The electron spin can therefore serve as a fast interface for control and readout, while the surrounding nuclear spins act as a longer-lived quantum memory. One way to imagine this is as a library. The electron spin is the librarian. It retrieves information, transfers it, and communicates with the outside world. The nuclear spins are the bookshelves where information can remain stored for a longer time. By controlling the interaction between the electron spin and these nuclear spins, the system can create entanglement and perform conditional quantum operations. Finally, the result must be measured. When another laser pulse is applied, the NV center emits a different amount of fluorescence depending on the electron spin state. A detector measures this light, and the system infers the qubit state from the brightness of the optical signal. In other words, SaxonQ's machine awakens the qubit with light, makes it calculate with microwaves, and then listens to its answer through light. Once again. But optical readout introduces an important difficulty. The number of photons collected from a single measurement may be small, and because quantum outcomes are probabilistic, the same circuit often has to be executed thousands of times, or even more, to estimate the final probability distribution accurately. This is where SaxonQ's multi-core strategy becomes important. SaxonQ's QC 2026 dual-core system contains 2 quantum processing cores. Each core is described as having 4 or 5 qubits. The 2 cores can execute different tasks simultaneously, or they can perform similar calculations in parallel. According to the white paper, the system is designed to operate in an ordinary room temperature office environment. Its warm-up time is less than 1 hour, and its power consumption is approximately 600 watts. The reported single-qubit gate fidelity reaches as high as 99.92%, while the 2-qubit gate fidelity is listed at approximately 97%. The system supports Qiskit and OpenQASM, as well as a graphical interface, job queue, and remote access. This approach resembles an important transition in the history of classical computing. For many years, the computer industry tried to make a single processor core faster and faster. But increasing clock speed eventually created serious problems involving power consumption and heat. The solution was to move toward multi-core processors, where several cores divide the workload. SaxonQ proposes something similar for quantum computing. Instead of forcing an ever-growing number of qubits into a single quantum chip, the company aims to build relatively small quantum cores, whose qubits can be controlled reliably, and then place many such cores inside one system. Because NV centers can be formed using ion implantation and semiconductor-style fabrication processes, the company argues that identical quantum cores could eventually be manufactured repeatedly. If several cores can share parts of the control electronics and optical infrastructure, adding another core may become less expensive than building an entirely new quantum computer. If this strategy succeeds, a quantum computer may no longer need to be a single gigantic machine located in a central facility. It could become a local quantum accelerator, installed wherever it is needed. But at this point, we need to confront a crucial question. If a system contains 2 5-qubit cores, is it truly a 10-qubit quantum computer? The answer is not necessarily. Imagine 2 separate rooms. 5 people are sitting in the first room, and another 5 people are sitting in the second. Inside each room, the people can communicate freely and work together. But suppose there is no door, no telephone, and no communication channel between the rooms. Can all 10 people conduct one unified meeting? Not really. There are 2 groups of 5, but no shared conversation among all 10. Quantum computers face the same distinction. Even if the 5 qubits inside each core can become entangled with one another, the 2 cores do not automatically become a single 10-qubit quantum register. Unless quantum information or entanglement can be transmitted between the cores, the system is better understood as two 5-qubit quantum computers, not one fully connected 10-qubit computer. This distinction matters even more in quantum computing than it does in classical computing. Classical information can be copied and transferred relatively easily. Data can be sent from one processor core to another and combined afterward. An unknown quantum state, however, cannot simply be copied at will. Preserving its phase relationships and entanglement while transferring it between separate cores requires a genuine quantum connection. That connection might involve a quantum bus, a photonic link, remote entanglement, a resonator, or some other coherent interface. SaxonQ also discusses the use of circuit cutting. In circuit cutting, a large quantum circuit is divided into several smaller subcircuits. Each subcircuit is executed separately, and the results are reconstructed using classical computation. This is somewhat like cutting a novel into separate sections, asking different people to read them, and then trying to reconstruct the full meaning of the story. If the chapters are mostly independent, the task may be manageable. But if every character and event is deeply connected across the entire book, dividing it into pieces creates an enormous amount of missing context. Strongly entangled quantum problems behave in the same way. The more quantum connections we cut, the more measurement combinations and classical post-processing are required to reconstruct the original result. The overhead can grow very rapidly. The SaxonQ white paper itself acknowledges that circuit cutting does not scale well for large, highly entangled problems. That is why we should never evaluate a quantum computer only by adding up its total number of qubits. A more important question is, how many qubits can actually participate in one coherent entangled quantum state? In quantum computing, numbers describe size. Connections determine capability. This does not mean that SaxonQ's multi-core strategy is useless. Not every computational problem requires one enormous entangled register. The first useful application is repeated measurement. A quantum computer rarely produces a reliable answer after running a circuit only once. Because measurement outcomes are probabilistic, the same circuit must often be executed thousands of times to estimate the probability distribution. Instead of running a circuit 1,000 times on one core, 10 identical cores could each run it 100 times simultaneously. In this case, multi-core quantum computing does not increase the size of the quantum state. It reduces the time required to collect measurement statistics. The second useful case involves independent tasks. A system could evaluate different candidate financial portfolios, compare several molecular structures, or test different machine learning parameters at the same time. If the tasks do not require shared quantum information, entanglement between the cores is unnecessary. The third application is multi-user access. Imagine a university quantum computing course. If dozens of students must share a single QPU, most of them will spend their time waiting in a queue. But with several independent cores, different students or researchers could run real quantum experiments simultaneously. From this perspective, SaxonQ is not necessarily trying to build the world's most powerful quantum computer first. It may be trying to build one of the world's most accessible physical quantum computers. The company also presents image classification and quantum machine learning as possible applications. An image can be divided into separate regions, with different cores processing different sections. The outputs can then be combined to produce a final classification. The white paper also describes a demonstration in which a small SaxonQ QPU classified whether a hand-drawn image represented a smiley face. Of course, this does not prove quantum advantage. Even an ordinary smartphone can classify a smiley face very easily. The meaning of the demonstration lies elsewhere. It shows that a user can provide an input, that the input can be converted into a quantum circuit, that the circuit can run on a physical NV center QPU, and that the output can be returned through an integrated software interface. This is not proof that the quantum computer outperforms a classical one, but it may be evidence that quantum hardware is moving from a delicate laboratory experiment toward a usable system. What then are the most important advantages of SaxonQ's technology? The first is room temperature operation. Eliminating the dilution refrigerator and ultra-high vacuum infrastructure is not merely a matter of reducing the electricity bill. It changes the size of the machine, the installation requirements, the maintenance burden, the warm-up procedure, the operating cost, and the level of expertise required to use it. The second advantage is physical robustness. Trapped ions and neutral atoms must be suspended and controlled in space. NV centers, by contrast, are fixed defects embedded inside the diamond lattice. They do not escape from a trap, and the basic atomic structure is mechanically stable. The third advantage is the possibility of using semiconductor-style manufacturing. SaxonQ describes the use of ion implantation and chip processing methods to create NV centers and control structures. The semiconductor industry has become extraordinarily effective at manufacturing the same structure repeatedly and at large scale. If quantum computers are ever to become industrial products rather than unique scientific instruments, reproducible manufacturing may ultimately matter more than one exceptionally beautiful laboratory demonstration. The fourth advantage is deployability at the edge. The current SaxonQ system is certainly not small enough to fit inside a smartphone. It consumes roughly 600 watts and occupies the space of a server cabinet. Even so, the absence of a giant cryogenic or vacuum system creates a meaningful difference. In the longer term, one could imagine quantum accelerators operating near factories, medical devices, autonomous vehicles, aircraft, robots, or security systems. Today, much of artificial intelligence runs inside enormous data centers. But when an autonomous car detects an obstacle, it cannot wait for a server hundreds of kilometers away to decide whether the vehicle should stop. The decision must be made locally. Quantum computing may eventually divide into two categories as well: giant cloud-based machines and smaller local quantum accelerators operating close to the problem. SaxonQ is placing its bet on the second possibility. Room temperature operation, however, does not solve every challenge in quantum computing. The clearest limitation is the number of qubits per core. The current Qiskit 2026 dual-core system is described as having only 4 or 5 qubits in each physical core. At this scale, it is difficult to solve problems that are beyond the reach of classical simulation. The second limitation is gate error. The white paper reports a maximum single-qubit gate fidelity of 99.92%, but the measured 2-qubit gate fidelity is approximately 97%. 97% sounds impressive, but quantum circuits may contain dozens, hundreds, or eventually millions of gate operations. If each operation has a 3% chance of error, the probability that a long sequence of gates remains correct falls rapidly. Imagine a musician who plays each individual note correctly 97% of the time. A short melody may still sound acceptable, but in a symphony containing thousands of notes, small mistakes accumulate. Quantum computation behaves in much the same way. Shallow circuits may remain usable, while deep circuits become increasingly unreliable. The SaxonQ white paper also presents pulse optimization results suggesting multi-qubit gate fidelities above 99%. However, some of these values are simulations rather than full experimental benchmarks across the physical system. They must therefore be confirmed repeatedly on actual hardware. The third limitation is readout. The ability to read a spin state optically at room temperature is a major advantage. But if only a small number of photons are detected during each measurement, the circuit must be repeated many times. For time-critical applications such as vehicles or electrical grid control, fast quantum gates alone are not enough. The entire time to solution matters. Initialization, gate execution, readout, data transmission, classical processing, and final decision. The fourth challenge is precise placement of NV centers. To create strong interactions between separate NV centers, they must be positioned very close to one another. But as they become closer, individual control becomes harder. Their signals may overlap, unwanted interactions may increase, and optical or microwave crosstalk may become more serious. People face a similar problem. If they are too far apart, cooperation becomes difficult. If they are crowded too closely together, they interfere with one another. A scalable quantum chip must find a balance between strong coupling and precise individual control. The fifth challenge is manufacturing yield. Implanting nitrogen into diamond does not guarantee that every implanted atom becomes a high-quality NVR qubit. The defect must form in the correct position. It must have the proper charge state and crystallographic orientation. The surrounding material must not contain too much unwanted damage. Its coherence time and optical behavior must also be sufficiently uniform. Creating one excellent qubit is very different from producing thousands of nearly identical qubits reliably. Finally, there is the challenge of quantum error correction. A truly general-purpose quantum computer cannot be built merely by increasing the number of physical qubits. Many physical qubits must be combined to create logical qubits that can detect and correct errors. The SaxonQ white paper provides a roadmap for increasing physical qubit and core counts, but it does not yet provide a detailed fault-tolerance architecture. It does not clearly specify which error-correcting code will be used, how many physical qubits will be required for one logical qubit, or how quickly repeated error syndrome measurements can be performed. This is the largest bridge separating a room-temperature quantum processor from a fault-tolerant quantum computer. SaxonQ also presents a highly ambitious scaling roadmap. The chart on page 9 of the white paper lists a target of 120 total qubits in 2026, more than 1,000 in 2027, and more than 10,000 by 2030. The plan is to increase both the number of qubits per core and the number of cores in the system, potentially reaching 128 cores. These numbers are impressive. But the same white paper describes the current Qiskit 2026 dual-core product as containing 2 physical cores with 4 or 5 qubits per core. Therefore, the figures of 120, 1,000, and 10,000 qubits should be interpreted as future development targets, not as specifications already demonstrated in the current machine. Several quantities must also be distinguished carefully. Are the cores physical or simulated? How many qubits within one core are fully entangled? Is the total merely the arithmetic sum of all physical qubits? Can quantum states be transferred between cores? And how many error-corrected logical qubits does the system provide? A city may contain 10,000 people, but that does not mean all 10,000 can participate in one conversation. Without roads, communication networks, institutions, and shared rules, they remain a collection of separate individuals. A quantum computer is similar. The number of qubits matters, but the architecture connecting them matters even more. For SaxonQ to succeed in the long term, it must do more than increase the number of independent cores. It must develop a way to create genuine quantum links between them. This may require photon-mediated remote entanglement, optical interfaces, resonators, or some form of quantum bus. Only then can the multi-core architecture move beyond parallel execution and become a truly modular quantum computer. Can Saxons compete with companies such as IBM or Google? If we compare only qubit count and large-scale general-purpose computational capability, the gap is currently substantial. IBM and Google are pursuing larger superconducting processors and fault-tolerant logical qubits. Trapped ion companies emphasize very high gate fidelities and flexible qubit connectivity. Neutral atom platforms are building arrays containing hundreds or even thousands of atoms. SaxonQ is pursuing a different strategy. Rather than trying first to build the most powerful quantum computer, it aims to create one of the easiest quantum computers to install and operate. Rather than maximizing raw qubit count alone, it seeks to bring quantum hardware closer to real-world environments. Its most realistic short-term markets may include university education, corporate research, quantum algorithm testing, multi-user on-premises QPUs, and systems that combine quantum computation with quantum sensing. For a university or company that wants to own and operate physical quantum hardware directly, a system without a dilution refrigerator may offer real value. But for large-scale quantum chemistry, cryptographic attacks, or deep fault-tolerant circuits that require many globally entangled qubits, the platform still has a long way to go. It is therefore not enough to say that SaxonQ has fewer qubits than IBM. A racing car and an urban electric vehicle should not be judged by exactly the same standards. A city car is not worthless because its top speed is lower, but it should not be advertised as faster than a racing car either. SaxonQ's greatest value may not lie in solving the same problems as the largest cloud quantum computers. Its value may lie in bringing quantum functionality into education, research laboratories, factories, and industrial devices. When we look back at the history of computing, we see a fascinating pattern. The earliest computers filled entire rooms. Then computers moved onto desks, onto our laps, and eventually into our hands. The history of machines is not only a history of increasing power, it is also a history of increasing proximity. Quantum computers, however, seem to have returned us to the age of room-sized machines. They remain enclosed in refrigerators, vacuum chambers, laser systems, and complex wiring. SaxonQ's challenge is therefore larger than the engineering of diamond qubits. It is asking a deeper question. Can quantum computers leave the laboratory? Instead of connecting to a distant quantum data center, could we one day bring the quantum computer into our car, factory, hospital, or research institute? Technological revolutions do not always begin with the most powerful machine. Sometimes a less powerful machine changes the world simply because more people can actually use it. The first personal computers were not stronger than the mainframes of their era. But once computers appeared on ordinary desks, the social meaning of computing changed. The first smartphones were not the world's most powerful computers either, but they allowed us to calculate, communicate, and access information wherever we went. The true turning point in quantum computing may likewise not be the day when the largest quantum processor is completed. It may be the day when small but usable quantum cores begin appearing throughout laboratories, factories, vehicles, and industrial systems. So how should we evaluate SaxonQ? The technology is not fictional. NV centers are real quantum systems that can be controlled at room temperature. Their electron and nuclear spins can store, manipulate, and read quantum information. SaxonQ has taken this platform from a delicate laboratory experiment toward an automated product and has demonstrated the operation of two physical cores inside one integrated system. Room temperature operation, compact infrastructure, ordinary electrical power, semiconductor-style fabrication, and parallel user access are genuine differentiators. But the current SaxonQ machine should not yet be described as a large-scale universal quantum computer. The number of qubits in each core remains small. 2-qubit gate errors are still significant. Quantum links between different cores have not yet been clearly demonstrated as part of the product architecture. And applications in image classification, vehicles, medicine, and industrial AI remain future possibilities rather than evidence of proven quantum advantage. 4 questions will determine the future of this technology. First, how many qubits can be entangled within a single core at high fidelity? Second, how quickly and accurately can those qubits be initialized and measured? Third, can separate cores move beyond classical parallelism and become quantum mechanically connected? And fourth, can the platform solve a real industrial problem faster or with less total energy than a GPU or an advanced classical algorithm? When experimental answers to these questions begin to accumulate, SaxonQ may move from being an intriguing room-temperature quantum device to becoming a genuine industrial quantum computing platform. What we are seeing today is not yet the completion of the quantum revolution. It is closer to the moment when quantum computing first begins knocking on the door of the world outside the laboratory. And perhaps the machine that changes the future will not be the largest one. Perhaps the first quantum computer to transform society will be the one that can come closest to us. Thank you for watching, and please subscribe. From ThothSaem's Physics.